Okay. Good morning, everybody. Welcome. Hi. Pretty good. Are you keeping warm? It's a really cold morning when I woke up. I saw frost on the roofs of buildings and things. I have Albert's working on one of the HDMI cables right now. Jonathan's working on setting up the dominoes. I don't know if you've ever seen this row of increasing dominoes. And there's this crazy guy who's a friend of mine named Stephen Morris who knocks over the tiniest domino, and then there's a chain reaction which knocks over the biggest domino. It is a meme, and these are the exact dominoes from that meme, by the way. We've had them for a while, and I'm going to set that up. Do that. Idea being that you have some potential energy, which is getting stored, and then you can release that gravitational potential energy and create kinetic energy, which can then be used to set up a chain reaction. But remember from Friday, I was going to collide these two cars and see if we could figure out who's at fault. There was a yellow Hummer driving south, colliding with a blue Toyota driving east. The speed limit was 50 kilometers an hour, and after the collision, the two cars stuck together, so we're going to call this a totally inelastic collision in the parlance of Chapter 7, actually, if you've read that far. The police measured that the skid marks are a 10-meter-long line angled 32 degrees east of south. So let's start sketching this out. The first thing I'm going to do is assume that there's no external impulse during the collision. So there's sort of, again, two segments of the motion here. There's the sliding kinetic friction, which, of course, there will be an external impulse of friction. But during the collision itself, when the two cars are crashing, you've got J is equal to 0, and so P initial equals P final. And these are vectors, so there's going to be an X component and a Y component, so we have to set these up. Okay, so initial. We've got, let's put the Hummer driving south. The mass here we know somehow. Maybe we look it up. 3,900 kilograms. The velocity in the y direction. So I'm going to do, by the way, I'm going to define plus y is like north. And I'm going to define plus x is east. So Vy initial, that's actually what we're trying to find just before the collision. And then but I guess that Vx initial equals 0. And then the Toyota is going directly east, and the mass of the Toyota is less, 1,200 kilograms. And Vx initial is the thing we're trying to find, and Vy initial of the Toyota equals 0. And then the final situation, you have this kind of conglomerate of a Toyota crashed in with a Hummer, which is now moving at some velocity, which is going to be the same direction as that big, long skid line that's on the pavement. And so I'll put this V final. And I think there's an angle east of south, this theta. Theta is equal to 32 degrees. There's south, there's east, so it's that sort of direction. This is the V final of the collision. And it's also going to be the V initial of that sliding friction part. So equals V initial of, I guess I'll call it the skidding. So the idea here is that kinetic friction causes the combined mass to slow as it skids. And so there's going to be some V initial, and it's going to go D is equal to 10 meters. And then this V final here is going to be 0. It's going to start with the speed right after the collision. It's going to slide for a while, then it's going to stop after 10 meters. So we can use kinematics for that part of the problem to solve that. Okay. So there's two segments of motion. One is the collision, and 2 is the skidding. So V final of 1 equals V initial of 2. So let's start, actually I'm going to start from the end. Let's start by analyzing segment 2. Because that's going to be we're going to find that V initial just from kinematics, and then we can plug that in and try to figure out what we can about the initial speeds, kind of working backwards. Segment 2. So let's do a force diagram of that combined sliding mass to find the system of the combined mass. So that's going to look sort of like this. You've got the normal force, you've got the m total g, and then you've got I guess it's going this direction, the initial, but the acceleration is backwards because you've got the force of kinetic friction acting to the left. So what we say is the sum of all the forces vertical or something. I'm sort of drawing this from the left here, it's a bit weird. Is 0, and that means that the normal force is equal to m total g. And if we call this like the d direction or something, plus d, then the sum of forces in the d direction, it's a little weird because I defined y to be north and x to be plus when I was thinking about the collision, but now what I'm doing is looking at this from the side just to get this skidding part. So the variables are a bit messed up here. Minus mu sub k times n, which is going to be minus mu sub k times m total times g. So the acceleration in this d direction is going to be the sum of all the forces divided by m total. And you get negative mu sub k m total times g divided by m total. The m totals cancel there. So the acceleration is just mu sub k times g. So you get 2AD is equal to V final squared minus V initial squared. So V initial is equal to the square root of negative 2A times D. You get the square root of 2 times mu sub k times g times d. And we know all those things, I think. So the police could measure mu sub k, and that d is the 10 meters. Okay. So now we're going to go back to the collision, and I can write down the two. Let's do these little what are they called? Momentum bar charts. You've got P initial in the x direction plus J in the x direction equals P final in the x direction. So for x, it looks kind of like this. You've got the Toyota plus the Hummer plus no external forces equals this positive x component of the total combined mass. And then in the y, you've got sort of the opposite. You've got this is the Hummer. You've got the Toyota is not moving in the y direction. The Hummer has some, actually negative, right? Should have drawn this up like that. Plus 0 impulse. And so this is going to have some big negative P final in the y. P initial in the y direction plus the jy equals P final y. So for x, I would just say that the mass of the Toyota times V Toyota initial plus 0 equals the mass total, the combined mass, times V final. Times sine theta. And for the y direction, you got 0 minus mass of the Hummer V Hummer initial plus 0 equals negative mass total times V final cos theta. So this is, we'll call that equation 1 and equation 2. So 1 implies that the V Toyota initial, which is what one of the things we're trying to find, mass total divided by mass of the Toyota, times 2 U sub k times g times d. We can find the V final from that previous segment, times sine theta. And the y component gives us the Hummer, m total divided by mass of the Hummer. Again, times that V initial, which we found from before, times cosine theta. And so you can get, for example, V Toyota initial, you can work it out, 1,200 plus 3,400, that's the total combined mass, divided by the Toyota mass times square root of 2 times 0.8 times 9.8 times 10. And don't forget to multiply by sine of 32 degrees. I ended up getting 28.2 meters per second. And if I times that by kilometers, divide it by 1,000 meters per kilometer, and multiply it by 3,600 seconds per 1 hour, I'm a little curious how fast that is. You get 102 kilometers per hour. And it's a 50 zone. So that's speeding. And also the V of the Hummer initial, I think, equals 13.9 meters per second. And so I think what's going on here is that the Toyota is at fault. He was really, really speeding. Is there any progress with that laptop 1 HDMI, or how's it going? No? Okay. How are you guys doing? Everybody's happy? You're good? Okay, great. All right. The lights are a little better. You can still see. Okay, let's do a top hat question. I'm just going to start it here. Doesn't matter if they can't see it. Yeah. I think what I'll do is, so this is a weird kind of one. It does require you to work something out, but a lot of the numbers are 1. If you had a 1 kilogram block drop from a height of 1 meter above the floor, and when it collides with the floor, it takes 1 millisecond to stop. So we would call this, I guess, an inelastic collision, because it ends up stuck to the floor. It doesn't bounce. What was the magnitude of the average force of the floor on the block during the collision? So this is a Chapter 6C kind of problem. Even though we're going to start Chapter 7 in a minute, this is a Chapter 6 review. So see if you can do it. Maybe I'll put 2 minutes on the clock here. Perfect. That's what I want to show, actually. 15 seconds to click one of these in. Sorry for the time pressure on a Monday morning. You can always do them afterwards. Okay. And then I'll work through it. Well, let's do it 1 sec. We'll give it a try as soon as we see what the results are, and then because I do want to flip over. Ooh, okay. So a lot of people are voting for E, and I can tell you that when I worked this out, it's not at all obvious, but that is what I got. Do you guys want to try it? Press the select button. Amazing. Thank you so much. Okay. So free fall, a distance of h at the acceleration is 9.8 meters per second squared. So I would treat that as like a kinematics thing. And then segment 2 is the collision with the floor. And that's a chapter 6 thing. I guess you could do that as a kinematics issue as well, but it's maybe a little faster to do it the chapter 6 way. So I'll start with segment 1. We'll use an old chapter 2 equation. 2AH equals V final squared minus V initial squared. It's dropped from rest, so this is equal to 0. So you get V final square root of 2 times G times H, and that's square root of 2 times 9.8 times 1. So when I got that V final of segment 1 is equal to 4.43 meters per second, and then that becomes the V initial, V final of 1, do segment 2, equals V initial of segment 2. And the V final of segment 2 equals 0. So again, we could probably use kinematics for this one and somehow just figure out the acceleration and then multiply it times the mass and get the force. But let's do it using, I guess there's this P initial in the y direction, plus some external impulse from the floor. J in the y direction causes it to stop. P final in the y direction. And so I've got P initial y plus J sub y is equal to P final y, which is equal to 0 because it stops. Negative M V initial 2 plus the force in the y direction, delta t, is equal to 0. So I'm getting a little mixed up with my minus signs, but it's going to be V that you found divided by delta t times mass. So you multiply by 1, multiply by 4.43, and divide by 10 to the minus 3. And that's where the 1,000 comes in, and I got 4,430 newtons. It's about 4 kilogram meters per second was that initial momentum. And when you divide by 1,000th, you get 4,000 newtons is what's required to stop it in a millisecond. Okay. So good work on that. This morning's pre-class quiz, a ball was thrown straight upward. How does the sign of the work done by the gravitational force while the ball is traveling upward compare with the sign? So basically, there's this idea that if you consider the Earth to be outside the system, then there's an external force which is doing work on the motion, which is, I guess, what's causing it to slow down. So this is when you don't consider gravitational potential energy. That's the reason it slows down. So negative work on the way up, positive work on the way down. We'll talk more about that later today. An object weighing 20 newtons moves horizontally towards the right a distance of 5 meters. What's the work done by the gravitational force? So we're going to talk about a little bit about this as well, but when that lady was carrying the briefcase or something, if there's a force which is perpendicular to a displacement, then it does 0 work. 2 identical balls are thrown upward. The second ball is thrown with initial speed that is twice the first ball. How does the maximum height? So the idea here was that, I guess, initial, I'll write this down a little bit. The initial is that you've got 1/2 mv initial squared plus mg y initial. And then the final, this is a conservation of energy problem, is 1/2 mv final squared plus mg y final. That's the way I like to write these things down. The initial energy equals the final energy. And so initially the y, I think, equals 0. And at the end, when it's at its maximum height, then the final speed will be 0, max height. So when you get rid of the zeros, you get that 1/2 mv initial squared equals mg y final. So 2 times the v initial will go to 4 times the y final. So someone asked, as Earth is orbiting the sun, its movement is approximately circular, so the force the sun exerts on the Earth is perpendicular to the Earth's orbit. Or I guess any little displacement of the Earth goes perpendicular to the direction of the force on it. So the question is, does the sun do work? And the answer is no. That's exactly right. If you've got uniform circular motion, then that radial force is neither speeding up the object nor slowing it down, so you have zero work done by radial force. It's a really excellent question. When forces do work, they tend to either speed up an object or slow it down. At least that's what they're trying to do. And since all you're doing is turning it, then you're not doing any work. Same student. Second, what's the relationship between kinetic energy and momentum, as they are both related to mass and velocity? I didn't put this on the animation, but I guess that's one equation. It's not used very often, but this is sort of combining our new equation, 1/2 mv squared, with our old equation, P equals mv. So there is an equation. Okay. I don't get why an object has no gravitational energy if Earth isn't included in the system. So the idea, I think, with this, it's a bit strange, but in your book at Kina, they're very careful to talk about a force. Forces always come in pairs. They always describe an interaction between two objects. So when you talk about the gravity force, mg, that really is an interaction between me and the whole Earth. And so if you're going to write down this equation, mgy, this term in your equation for energy, you're implicitly including the Earth in your energy because there's an interaction there that includes the Earth. So, okay. There's a happy birthdays off to Hunter and Isma. Happy birthday, and rock on. Also, I don't know, Brendan, if you're here, but you mentioned that it's your anniversary, so tomorrow, so 14th anniversary, that's pretty amazing. Apparently Jen's not here, but yeah, we'll do a happy anniversary. Married a little longer than me. So, okay. So we're getting into energy. Energy is a property of an object, like age or height or something like that. Something has some energy. Every object that is moving has some kinetic energy, and any object that's in the gravitational field has some gravitational potential energy, or I guess you would say that the system of the object plus the Earth has some gravitational potential energy. Has units. We can write it down here. It's called, the SI unit of energy is called the joule. I'm not really sure why the SI unit of momentum never got its own name. Maybe it should be called the Harlow, but no. Okay. Energy has its, I guess this is a kilogram meters squared per second squared. It's relative, meaning that the kinetic energy of an object is relative to the observer. So if you're standing and a car goes by you, you would say the kinetic energy of the car is big, 1/2 mv squared. If you're in the car, then relative to you, the kinetic energy of the car is 0, because it's not moving relative to you. You'd say the kinetic energy of that tree coming towards you is high. There's an equation for kinetic energy. Let's just check the units here, by the way, since we have now an equation. I think it's going to be, the half doesn't have a unit, but it's got kilograms and then meters per second all squared. So it's going to be kilograms times meters squared per second squared equals joule. Okay. And then gravitational potential energy. So that's the energy of motion. An energy of position is usually called a potential energy. There's going to be two that we'll use. One is mgy, where g is this 9.8 meters per second squared. But basically, when you're up on the roller coaster high up, you've got all this gravitational potential energy. As you go down the roller coaster, the value of y decreases, and so your gravitational potential energy decreases. But at the same time, your kinetic energy increases. It gets converted. There's another potential energy called the elastic potential energy, 1/2 K times x squared, where K is a spring constant. So if something's attached to a spring with some spring constant in newtons per meter, then, and you stretch or compress the spring, then you can have some potential energy stored in the spring. X here is the distance, the end of the spring is displaced from equilibrium. So the other kind of energy that gets lost all the time is this heat energy. And I don't know if you remember when we set up that infrared camera on the table and I kind of rubbed my foot on the floor, it heated up the floor. So there's a sort of a thermal energy. Atkina calls it the internal energy, U sub internal. So U, she likes to use the letter capital U to represent energies that are potential or something, and the capital letter K to represent 1/2 mv squared. But it's proportional to temperature. If something heats up higher temperature, it means it stores more internal energy. Okay. And this is that meme I was telling you about. We're probably going to switch. I have to do the HDMI, but basically, a domino is a rectangular solid, and you can stand it up on its edge. And when it's standing upright, if you look at its center of mass, it's higher. Its Y value is higher than if you tip it over. So that's a state of unstable equilibrium. If you tap it a little bit, it can start to lose its gravitational potential energy. That converts to kinetic energy, causing it to fall faster, and it can knock over another domino. And there's this, I guess, you can show, that a domino can knock over another domino that's up to 1.5 times bigger than the first domino. So you can imagine the sequence of dominoes, each one being 1.5 times bigger than the previous one. If I knock over the first one, it'll knock over the next one, et cetera. You got a chain reaction. Should we? So this is exactly what we've got here. There's a whole bunch of dominoes. The first one, if we can see it here, I got to be a little careful that I don't knock these over by accident. Maybe I'll put that one in a second. Can we see it? Okay. The first one is going to be, are we missing one? Is there one still in the bag? This first one is, you can just sort of see it here. It's just a cute little guy, about 8 millimeters high. Oh, you put that one in there. Careful. No safeguard. You just have to have a steady hand. So I'm going to balance this little guy here. Don't let it fall, Jason. Oh, it almost fell. Well, maybe we'll put him in last. It gets bigger and bigger and bigger, and the last one is over a meter high, and it's about 100 pounds. Ugh! So I have to push it up, and when I do that, I'm adding a whole bunch of gravitational potential energy to get it up to this height, right? So maybe, Jonathan, do you want to knock it over the last one? We'll maybe give you a countdown. The first one. 1. You move your hand a little, your left hand. There you go. 1, 2, 3, go. Oh, it didn't work. The smallest one is the hardest one. Let's do the second smallest one, maybe. Three, go. Thank you. Nice one. Idea being, it's a geometric progression. I think this is about 8 dominoes. Turns out if you had about 30 dominoes, then the last domino would be the size of the Empire State Building or something. So we have all this energy being released, but it was put in there when we raised up those dominoes to be standing upright. So you're storing energy with gravitational potential. So where did the energy come from? It comes from work. Work involves force times distance, and there's an equation for it. F is the force, D is the displacement. These are both vectors, so theta is the angle between those two vectors. So if you were to connect the vectors tail to tail, you would be able to measure an angle between them. So you always have to apply a force and move something to do work on a system. And it turns out that newtons times meter also equals joules. We'll do a couple top hat questions on this, but basically, idea here is that if you're holding a briefcase and you're moving it to the right, and you're pushing it to the right, if you, push a force to slide it along, then this force and this displacement are in the same direction. So I would say that theta equals 0 degrees. And so the work is equal to FD cos theta. The cosine of theta, cosine of 0 degrees, is equal to 1. So you get the work is equal to plus times F times D. And so the way I like to think of that is that the force that I'm applying in the direction of the displacement is trying to speed the object up. So I'm adding energy to the system. The work being energy transferred into the system is positive. If it's moving to the right because it has an initial velocity to the right, it's not because I'm pushing it, if you can imagine that, all I'm doing is supporting it against gravity or something, then that force is not changing the energy of the object. And mathematically, what I would say here is that theta is 90 degrees. And the cosine of 90 degrees, try that on your calculator, 0. So you would say the work is equal to FD cos theta. It's equal to FD times 0. So the work here equals 0. If the force you're applying is perpendicular to the displacement, then it does no work. And the last situation is that, this is a bit harder to picture. Imagine that the object is sliding to the right because it had some big initial velocity to the right, but you're trying to slow it down by pushing it to the left, but you're losing. So what that means is that the displacement is opposite the direction of the force. This can happen, like I say, if there's a big initial velocity that's giving it the displacement and you're not able to slow it down fast enough. Okay, hopefully you guys are following that. In that case, F is to the left, D is to the right, so what I think that means is that this theta is 180 degrees. And the cosine of 180 degrees, try that on your calculator, is equal to -1. So it means that work is FD cos theta, so work here equals negative FD. This is called negative work. You're applying a force to a system and you are reducing its energy. Probably because you're trying to slow it down. And this will actually happen sometimes if the external force is friction. If you got sliding friction acting on an object, it's going to reduce its kinetic energy. Okay. Let's do a couple questions here about Webhav doing a bench press. He slowly pushes a bar up a distance 0.3 meters while pushing upwards on the bar with a force of 200 newtons. So we're asking here in the question, how much work does Webhav do on the bar? You need a force and a displacement. Think about that. It's really sort of a conceptual question, but you can do a quick little calculation and then compare with your neighbor. Think, compare, share, please. Survey says 60, positive 60, which I like. See if this works out. Basically, idea here is that this force of, I guess, V on B or something is up, and the displacement is up. So this means that theta is equal to 0 degrees. So the work is just plus F times D. So it's just 200 newtons multiplied by 0.3 meters. Newtons times meters turns out to be a joule. And it's 60 joules. And it's a plus number. Next question, same exact bench press. He slowly lowers the bar down a distance of 0.3 meters while pushing upwards on the bar with a force of 200 newtons. Can you imagine that? If you just let go, it would fall. So instead, he properly lowers it slowly. I don't know. You have to imagine something that's going to fall on you. Maybe even your cat is above you, and you're lowering it towards you. You're pushing upwards, and it's coming down. So this is, the idea here is the force is 180 degrees away from the displacement. So you get that same 60, but now you get a negative F times D. Okay. So what's weird is that the bar, it would fall, and it would pick up kinetic energy, but you're doing negative work on the system and keeping it going really slow. So last question in this little sequence here is, Weber is doing a bench press. He slowly lowers the bar down a distance of 0.3 meters while pushing upwards on the bar. Then he pushes it slowly up the same distance back to its starting position. During the complete downward and upward motion, how much total work does Weber do on the bar? Okay. This is one of those weird physics concepts. Doesn't always match with your intuition. 10 seconds. Okay. See what people are saying here. 96% are voting for 0, and that's what I liked as well. So basic idea being that I think one way of thinking of this one is that, this is the last one here, that the displacement in this case equals 0. You're going up and down, returning to the same position. So you do 0 work. Work equals 0. Okay. So the idea here is that work is a way of transferring energy in or out of a system. So the sum of the initial energies in a system plus the work equals the final energy. And this may look very, very familiar to you because there was a chapter 6 equation that said the P initial plus, it wasn't work, it was plus the impulse equals the P final. So the purpose of impulse, a force times a time, is to change the momentum of an object. The purpose of work, which is a force times a distance, is to change the energy, I guess, of an object or a system. So I sometimes just put E initial equals E final, but the idea is that work done on the system can change the energy. Okay. So let's go through how they do it. So we have, actually, I don't know if, we don't have a video for this one. We'll just shoot it, right? So what we've got is a ball which is on a spring. And the whole idea, we can just pull the thing and launch it. I don't know if video people can center me for this one. Let's do a demo. 1, 2, 3, go. Whoop, whoop. Okay, goes up, falls back down. So I'm going to reload it again, try to see how high it goes. But there's actually 3 parts to the motion. There's the, or three positions that we're going to want to keep track of. One is this initial position, which is at some height, and it's 0 initial velocity, but there's a bunch of elastic potential energy stored inside the spring because the spring has been compressed. Then I'm going to release it. The spring will uncompress back to its equilibrium, but now the ball will be really going fast. And then the ball goes up and it eventually stops at some maximum height. We can do it again. Whoa! Way up there. And you can see now the spring has lost all its energy. It's in its sort of equilibrium state. By the way, this is a spring. So the idea is that the spring, if I stretch it, it has some potential energy. If I compress it, it also has some potential energy. Okay. So let's just analyze that a little bit. Yeah, we're good. Using these energy bar charts. So a spring-loaded toy gun is used to shoot a ball of mass m straight up in the air. The spring has some spring constant k. We define the system to be the ball plus the spring plus the earth, meaning we can use gravitational potential energy. There's the conservation of energy equation. And what we can do is kind of split up the energy into its multiple parts. So energy initial goes into 3 parts. Kinetic initial, gravitational potential initial, and elastic potential initial. And the final energy gets split into its 3 parts. Spring, or I guess the elastic potential, the gravitational potential final, and the kinetic final. And then there's work, which is force times distance. So here, the work done on the system is 0, I think. Kind of like when there's no external impulse. Everything here is internal. So we don't say that gravity does work because gravity is part of this system. And if we want to use energy bar charts, I would say for time A to B, what happens is that it starts with a whole bunch of spring potential energy bar charts. So that's the 1/2 k times xa or something like that squared. It also starts off with some negative potential energy because it's below, if we define y equals 0 here, this is h min, so it's actually minus mass times g times h min. And then it also starts with 0 kinetic and there's 0 work done. So plus 0 equals, the spring ends up with 0. The gravitational potential energy is 0 by definition. We have defined y equals 0 at that point A. And then it's moving. So 1/2 m times VA squared. So that spring potential energy has been converted some into moving the ball up a bit and some into speeding the ball up. And then it launches. So from B to C, what happens is that initially you got 0 spring because the spring is not compressed, 0 for the gravitational because you defined 0 at the point B. You've got all this kinetic, which is plus 1/2 m VB squared plus 0. And then at point C, you've got that it's, again, the spring is still uncompressed, so you've got 0. The gravitational is now all the energy. So whatever this initial kinetic energy was, it's converted to gravitational potential and plus 0. It stops. So you've got equals to mgh max. Okay. I think I will stop there. I'll see you on Wednesday. You should continue on with Chapter 7. In practicals this week, you're doing a collision. You're doing actually a Chapter 6 problem in which there's an external impulse coming from a fixed clamp on your cart, which will reverse its velocity, reverse its momentum, I guess. So I hope you have fun with that, and I'll see you Wednesday.